Hello, diamonds in the rough. So this will be a visualization video and kind of optional. So if you don't understand it, it's completely okay. And if you don't understand it, it is quite good for the next video. So it's kind of prerequisite. But I didn't want to introduce this concept this early. But I have to tell you. So we're gonna talk about decision boundary. What decision boundary are? This is nothing. This thing which I'm gonna tell you, it's not gonna help you with the modeling or understanding the data, understanding the math. It's just good for visualization. So it's not will help you in actual thing, but it's really good for teaching me for the stuff. So that's gonna help you. So let's get started. So if you see, if you remember from a previous data set, this was the data set we had for classification, and we were able to make a predict function. Normal predict function would not work. Uh, that you know the reason, and the reason is basically once we plot the data point, we see that our data is very weird. Like I cannot have a single line which can fit this data, and also predict zero or either one. There is nothing should be in there. So your none of the predictions should go over here, something like this. So this is the data we have, and fitting a line like this, a straight line is impossible. So you need some kind of curved line. We call it non-linear functions. Like any linear function is basically a straight line, which I'm talking about, mx plus c, which you remember from our slope videos, right? So same with any straight or linear function will probably not fit in this kind of data because they are too much segregated. So we didn't need a line which could fit these data points and these data points and have this S-shaped kind of curve that we already seen. Like this line will not work. It's a linear function. This line is basically a linear function with two values over here. This will probably not fit in. So we made it nonlinear by adding this sigmoid function. The sigmoid function, which is kind of a derivative of a kind, not derivative, it's like built on exponentials, right? So because of that, we got a beautiful S-shaped curve which can fit kind of this kind of weird data, right? Which is using classification regression, it would be simpler. So uh, one of the what do you say? One of the theta over here, the weight you can think like is used to find how much to curve like this. What is the angle of this curve? Another good thing you can think of as like placing it, like just like we have intercept values, right? Same way you can place where this curve should place. So this you can think like that. And this curve quite fits the data, right? All the zero class as in one class, and whatever the, like if I have to check for any predict like 1 comma 29, so this will over here, it will probably predict 1, something like this. So it quite fits the data. So this kind of theta we have to optimize. For that we use gradient descent, basically a slope method, kind of maximum minima, to solve our theta. But there is a, so this straight line function is made from two things. One is we have non-linear function, and then we have linear function. And what one of the beauty which I missed, not missed on purposely, I didn't want to confuse in the previous video, but on purpose I didn't told you that if I have to visualize this line, right, we can already see it like a shape curve. But if you just only focus on this straight line, this is the linear part. If I just focus on the linear part, the linear list line would create a kind of you can think of a uh, like a like a decision boundary. This is basically the decision boundary. So if you just print this kind of straight line, it will tell you what is the best line which segregate these data points, right? Our goal is to not find a decision boundary. Our goal is to fit the model where the losses are minimum. Basically, the more you closer to these data points your line is, the least loss it will be. But the goal is that only, but we don't have but there is a side effect of that goal is that this linear function inside our non-linear function, it kind of help you to visualize the data. Like in a classification problem, it will tell you how the data points should be segregated. So in this line we could see like this yellow line quite well segregate these data point. One could be a straight line over here, like this horizontal straight line, right? That could also be a good decision boundary. But this one tends to fits the, like it has like if you find the distance between all these data points with these yellow lines, it will be the farthest, something like this. So this is one of the one of the decision boundary. The more you will understand about decision boundary when we talk about SPMs, that there the actually concept of decision boundary makes sense. So there we will not be only be optimizing this what do we call it, the loss function, where our goal is to find the best weights. We will also making sure we have enough decision, like enough space between this line. So that will be a video for some another time, but I promise you that I will definitely make on that one. So that will do. But this decision boundary help you understand a lot of key concepts, like how we can make a neural network or non-linear function or something like this. Like how can we introduce non-linearity or multi-class problems. So these decision boundary will really help, and this decision boundary help us to understand a lot of concepts. So I hope you understand what decision boundary is. Just to summarize you, is basically our same predict function which we plot. Like the goal is to minimize the loss, and this is the S curve, but inside that you will see a linear part. If we plot that part, it kind of helps you to understand the decision, but basically tells you how this model has fitted the model and how far it is segregating the line. You will more understand it when I use it in another example, which will be coming forward in the next video. So I have to see you in that one.